Francois. I did hit that.
Okay, it's
Oh,
done.
I think I've got it. Good.
Let
I'll
me.
shut up.
Okay, now I've got to find you. Yeah, I'm not super. Oh, there you go. Okay, there you are. Now, can I minimize this? Excellent. Sorry, I'm not. Usually, I'm not in charge of doing this, so that's why I'm like, okay, how do I do it? If I just want speaker. Sorry. There's a way to minimize this. There. Okay, I think I've got it now. Okay, so well, thank you everyone for being here today, and thank you for inviting me. My name's Francois. I'm a paleontologist at the Royal Tyrrell Museum in Drumheller, Alberta. And then today I'll be talking. Yeah, I know this is an ornithology group. You're probably expecting me to talk about birds, but I'll be talking about actually the ancestry of birds, the origin of birds among small medium dinosaurs, and how birds got their wings and learned to fly. So thank you again for the great introduction. I'll just say again that, yeah, as mentioned, yet birds are dinosaurs the same way that humans are mammals. We don't usually say that humans evolved from mammals because we are mammals. Well, it's for the same reason, yeah, we should say that birds are dinosaurs, not that they evolved from dinosaurs, because they are a type of dinosaurs. And I'll show you that during this presentation. Okay, so I need to click on this. There we go. So of course, when people hear the word dinosaur, they think immediately of T-Rex or
Sorry.
Brontosaurus.
Francois, we're not seeing your screen. We're just seeing you.
Oh, okay. Oh, sorry. I'm sharing the wrong screen, I guess. Okay, how do I do that then? Okay. See, that's why someone else usually does that for me. Oh, there. Does this work?
Yes.
Yes, excellent. Thank you. Okay, now everything looks familiar. Yay. Okay. So yeah, as I said, yeah, when people hear the word dinosaurs, they usually think of animals like T-Rex. These dinosaurs look very different from birds, and people have a hard time understanding how it's possible for birds to be dinosaurs. But you have to think that there's hundreds of millions of years of evolution that separate a sparrow from T-Rex. So that's why it's not really surprising that these animals look very different from one another. There. So if we look at everyone's favorite bird, the Thanksgiving turkey that we see here, and then we remove all of its feathers, we eat all its muscles, and then we're left just with the skeleton, then we can see that there's over 10 characteristics of the skeletons that are listed in red here that are clearly indicative of a turkey being a dinosaur. And then in blue in the lower left, you have a list of other characters that you won't see in your roasted turkey because either the animal is already dead or some of its body parts have been cut off. But those characteristics are also indicative of the turkey being a dinosaur. So you don't have to memorize all of these. There's not going to be a pop quiz at the end. I just wanted to give you a sense that there's many, many, many characteristics of modern birds that are screaming dinosaur. I have to change here. But if we go back 150 million years ago and we look at the first bird, an animal called Archaeopteryx, we see that we're dealing with an animal that is transitional between modern birds and dinosaurs, an animal that's in between the two. So if we look at, there's 13 skeletons known for Archaeopteryx now, and if we look at them, we can see that this animal possessed 4 or 5 characteristics that are clearly diagnostic of modern birds. So we know that Archaeopteryx is a bird, but, oh, sorry. But if we also look at the skeleton, we realize that Archaeopteryx still possess 15 characteristics that are clearly seen in meat-eating dinosaurs, but not in birds. So those meat-eating dinosaurs, we call them theropods. And some of the most obvious characteristic of of meat-eating dinosaurs that we see in Archaeopteryx. I hope you can see my cursor here. This is the head of Archaeopteryx. It's an animal about the size of a pigeon, just to give you an idea of how big it is. But if you look on its jaw, you can see there's tiny little teeth in the mouth of Archaeopteryx. So that's clearly a sign that we're dealing with a small theropods. Here, this is the hand of Archaeopteryx. You can see it has long fingers with very sharp claws. Again, another characteristic indicative of a meat-eating dinosaur. And then if we look at the skeleton as a whole, we can see that Archaeopteryx has a long bony tail, something that no modern birds have, but that the meat-eating dinosaurs obviously possess. So all of this tells us that Archaeopteryx is a small carnivorous dinosaur, and the majority of differences that exist between modern birds and theropods have evolved after the advent of the first bird, after Archaeopteryx came to be. So when we say that Archaeopteryx and birds are dinosaurs, it's clear that they don't belong to any of these animals. Like those are the plant-eating dinosaurs. So Archaeopteryx and birds are meat-eating dinosaurs, theropods. But then when we look at, if we compare T-Rex to Archaeopteryx to the most famous of all theropods, T-Rex, we can see that there's major differences in terms of proportions and anatomy here. If we remove the feathers of Archaeopteryx and we just look at the skeletons, we see that there's major differences in terms of proportions and anatomy of these animals. So Archaeopteryx did not evolve from theropods like T-Rex. But here, if we compare the skeleton of Archaeopteryx to small meat-eating dinosaurs like Velociraptor of Jurassic Park fame, then we see that their skeletons are far more similar to one another. So this means they must have shared a very close common ancestor. But if we could have seen Archaeopteryx when it was alive, covered with feathers and colors and all, most people would have said that Archaeopteryx was a bird. It would have been a weird bird for sure, because it had clawed hands, a long bony tail, and it had teeth in its mouth. But it would have been a bird nevertheless, because it was covered with feathers and had wings. But this idea that Archaeopteryx must be a bird because it's covered with feathers and had wings is due to the perception that we have that dinosaurs were reptiles and thus they must have been scaly animals. This notion goes back to the 19th century with the discovery of the first fossilized dinosaur bones, when people at the time believed that dinosaurs were snake-like reptiles that lived in swamps, or gigantic lizards that were crawling on the ground. Then in the mid-19th century, when world-renowned anatomist Sir Richard Owen formally coined the name dinosaur in 1842, these animals began to be reconstructed as four-legged beasts in an upright posture and more like elephant-like proportions. So that gave them a far more mammalian appearance than previously considered. And then it's with the discovery of the first North American dinosaurs in the second half of the 19th century that our perception of dinosaurs started to dramatically change. From lumbering beasts, dinosaurs were now reconstructed as animals with an upright posture, similar to humans. And here's another one where there's biting a poor little hadrosaur here lying down on the ground. So you can see that the appearance and the posture of these animals started to move away from being lizards. With additional discoveries, dinosaurs finally reached towards the end of the 19th century and the beginning of the 20th century, an appearance that is familiar to most of us because these illustrations have filled children's books until the early 90s. But that's not to say that mistakes weren't made along the way. So for example, at one time we thought that the long-necked sauropods were crawling on the ground or living in swamps, that some dinosaurs were covered with spikes on their backs, or that, yeah, Tyrannosaur took down big duck-billed dinosaurs by kicking them in the gut to feed on them. So There's some mistakes that were made along the way, but overall, we had a pretty good impression of what dinosaurs looked like. Overall, the reptilian appearance of dinosaurs was fully established by the early 20th century. And despite the view that dinosaurs were sluggish swamp dwellers, already in those days, you could see that some paleo artists started reconstructing them as being very active animals, not necessarily sluggish swamp dwellers. The reptilian appearance of dinosaurs would remain unchallenged until 1998 with the discovery of the first feathered dinosaurs. These three dinosaurs discovered in the early Cretaceous rocks of China, going back about 125 million years ago, opened our eyes to a previously unknown look for dinosaurs. Because we found on the skeletons the impression of hair-like filaments preserved along the bodies here of the animals, and some rigid shafted veined feathers. You can see here a central rachis and the veins branching out in different direction on those feathers. So those feathers were found on the arms and tails of the animals. So it showed that some dinosaurs were not scaly critters that looked like reptiles, but were instead covered with feathers, just like birds. Of course, these discoveries made the cover of scientific journals and popular science magazines alike, and they have irrevocably changed the way we think of dinosaurs. But these discoveries were not to be the only ones made, and numerous other specimens of feathered dinosaurs have been discovered since 1998. Such a way that today more than 50 different species of feathered dinosaurs are known. But if we look at to which group they belong, we see that the vast majority of these animals are theropods in red, or meat-eating dinosaurs. There are very few plant-eating dinosaurs that were covered with feathers, at least very few that we know of. Among the feathered theropods, we can recognize a few famous ones, like here, some distant relatives of T-Rex were feathered. And then there's also another household name that you've heard of, Velociraptor of Jurassic Park fame, was a feathered dinosaur. So when the first Jurassic Park movie came out in 1993, Velociraptor was represented as a scaly dinosaur because the movie was made a full 5 years before the first feathered dinosaur was discovered, and 14 years before we found evidence of feathers in Velociraptor. So that's why Velociraptor looked like a scaly reptile. But now that we know it was covered in feather, it's time to update the look of Velociraptor in light of scientific discoveries. Instead of looking like this, Velociraptor may have looked a little bit more like something like this. Or if we want to add some patterns and color differences, maybe something like this. Although we don't know the exact coloration of the plumage in Velociraptor, we know that reconstructing it as a scaly predator is wrong. So the next time you see a representation of Velociraptor as a scaly animal, you should get mad, because now you know it goes against scientific evidence, the knowledge that we have based on fossils. So if you're part of the group of people, some people think that dinosaurs look scarier without feathers, so that's why they prefer them that way. Well, just remember this: reconstructing dinosaurs as scaly reptiles is equivalent to saying that chickens look like this. So it's no wonder that people that think that scaly dinosaurs are scary, because a featherless chicken is something very, very freaky to look at. So that's why scaly dinosaurs look scarier than feathered ones. In reality, Velociraptor would have looked a little bit more like this, like it would have looked like an angry bird with wings. So by plotting the distribution of known feathered dinosaurs on an evolutionary tree of dinosaurs, we can better understand how the evolution of feathers occurred among dinosaurs. So here I'll just give you a little bit of an orientation. From left to the right, we have time. So Triassic is the beginning of the age of the dinosaurs. The Cretaceous is the end of the age of the dinosaurs. Above the red line, you have all the meat-eating dinosaurs. And below the red line, you have all the plant-eating dinosaurs. And here in the green box, we have the birds that are nested way high up in the family tree, the theropod, the meat-eating dinosaur family tree. So if we plot in red the occurrence of feathered dinosaurs on the dinosaur family tree, we see that the greatest concentration of feathered dinosaurs occurs in the lineage leading towards birds. There are very few species of very few species of feathered plant-eating dinosaurs. So given the large concentration of feathered dinosaurs that we find in the lineage leading to birds, we can finally attempt to answer questions that were first raised in 1861 when the first skeleton of Archaeopteryx was discovered. How did the birds get their wings and how did they learn to fly? So first we have to look at the types of feathers that dinosaurs possessed. So if we look at the dinosaur skeletons, we recognize that there are several types of feathers, but they can be grouped into two broad categories. There are filamentous feathers and there's rigid shafted feathers. The filamentous feathers that you see here, they look a lot like fur or hair, and they covered the body of dinosaurs. Filamentous feathers are usually found in the more primitive species of dinosaurs because they were the first type of feathers to evolve. You can see that they look very similar to down feathers that we see in modern birds. You can see they're not identical, but they're very similar to down feathers that modern birds have. And just like down, the primitive filamentous feathers were probably used for insulation to keep the dinosaur warm or to keep it cool. And then there's the other kind of feathers that are found in dinosaurs. Those are rigid shafted feathers. So there's feathers that have a central rigid rachis, and then sometimes they have barbs that are branching off that rachis. So these feathers are usually found in theropods that are closer to birds. And those feathers cover the arms, the legs, and sometimes the body of dinosaurs. Some of those feathers are very similar to contour feathers or flight feathers that we see in modern birds, while there's other types of rigid shafted feathers that are unlike any other types that we see today. For example, here we see on this little dinosaur, you can see its body is covered with small filamentous feathers, but if you look on its tail, you can see it has large ribbon-like feathers that attach to a small bony tail. So it probably would have looked a little bit like this. So these feathers, we don't have that type of feathers nowadays, but it's based on their position and their appearance. There's very little doubt that those feathers were probably used for display and courtship, probably like the feathers on a peacock's tail, but were not used for flying. Then again, there's some rigid feathers that were exactly identical to modern bird feathers. And those feathers were found, as you can see here, on the arms and even on the legs of those small meat-eating dinosaurs. Those feathers would have allowed the animals to glide. And we know that even some of those small dinosaurs were actually capable of flying, although they weren't as good as the first birds, but they managed to evolve the flying capabilities. So, and it is the study of rigid shafted feathers and their distribution in the family tree of dinosaurs that can shed light on the origin of wings and the origin of flight. There's three main hypotheses that have been proposed to explain the evolution of wings and flight in the dinosaurian ancestor of birds. The first hypothesis is called the ground-up hypothesis, and it states that wings first evolved among ground-dwelling predators. So these animals had to pounce and jump to capture prey, and the evolution of wings would have allowed these animals to maybe jump a little bit higher or jump a longer distance or cover more ground to capture their prey. And then with time and evolution, these animals would have learned that by flapping, they could cover longer distances, and eventually that would have led to flight. Here you have a little drawing that shows that basically first you have feather wings that are just used to try to pounce and capture prey, but then with time that led to the evolution of true wings. So if this hypothesis is accurate, we would expect to observe wings in all growth stages of dinosaurs, whether they're very young animals or adults. Wings should be present because they would have played a crucial role for prey capture in animals of any ages. The second hypothesis is called the tree down hypothesis. It states that wings would have first evolved among arboreal or tree-dwelling animals. So primitive wings would have allowed animals to either parachute down to the ground or maybe to glide from tree to tree in search of food. And then with time again and evolution, animals would have glided over longer and longer distances to capture their prey, and eventually they would have learned to flap their wings and to truly fly. So if this hypothesis is accurate, again, we would expect to observe wings in animals of all growth stages, and to be present also in very young animals, because they would have needed wings to survive a fall from a tree, for example. And finally, there's a third hypothesis that was suggested maybe 20 years ago that's called the wing and assisted incline running hypothesis, or the WARE for short. And it states that wings would have evolved among ground-dwelling animals, not to fly, but to help them climb steep obstacles to catch prey or to escape predators. So something that supports that hypothesis is that behavior is actually observed in modern birds. So if you look at ground-dwelling birds that they need to climb up a steep slope or climb up a tree, they'll start flapping their wings, not to fly over the obstacles, but quite the contrary, to push themselves down so their feet have more traction against the trunk of the tree, so that they have more traction to climb up a very steep angle. So here's a video that the researchers have filmed in their lab that shows that happening. You can see these animals are flapping their wings exactly the same way as if they were trying to fly, but instead of generating lift, pushing air down, they're actually pushing air up and then pushing their feet into the substrate so they can climb steep obstacles. And you'll have a picture here. You'll see that doesn't only happen in the in lab. It also happens in the wild. Here you have a small baby bird that actually is flapping its wing to climb up a tree there. So again, if this hypothesis is accurate, we'd expect again to observe wings in individuals of all ages, from young individuals all the way to adults, because all animals need to escape predators. So the wings would have been beneficial regardless of age of the animal. And indeed, you can see on this picture here that there's even small birds that are incapable of flying actually beat their wings, flap their wings to gain traction against an obstacle and be able to fly up. So you can see here this four-day-old chick there is flapping its wing and actually using it to climb up an obstacle. But which of these three hypotheses is the right one? The three hypotheses were considered the main scenarios for the origin of wings, and the debate was still raging on until 2012, about 13 years ago. Prior to 2012, dinosaur skeletons associated with feather impressions had been found exclusively in the Old World and primarily in China. But then in 2012, myself and a team of collaborators have announced the discovery of 3 feathered dinosaurs in the Badlands of southern Alberta. So the two specimens were found in the Badlands close to the town of Drumheller, situated about an hour and a half northeast of Calgary. And those rocks are about 72 million years old. And then another skeleton was found in Dinosaur Provincial Park, about 2.5 hours southeast of Calgary. And the rocks there are about 76.5 million years old. And for those of you who aren't familiar with the landscape of southern Alberta, here is what Badlands look like. They're a unique landscape of rounded hills and deep, steep canyons produced by erosion, where there's limited vegetation and a lot of bedrock exposure. It's the playground for paleontologists. We love to climb up those hills and look for fossils that are eroding out of the ground. So you can see here, this is bone. This is part of a jaw of a duck-billed dinosaur. So that's the jaw, and here, those are the teeth there. So once the bones have been found and they look promising, paleontologists start digging, opening up quarry, and sometimes they need to dig into the side of hills because they're not always found way down in the flats. So then that's when paleontologists start carving out blocks of rock in which the bones are encased, and then we cover them with plaster and burlap to create a hard protective shell to protect everything during transport back to the museum. The blocks are brought to our preparation lab, where we have technicians that use a variety of tools, like air scribes, which are essentially mini jackhammers to carve away the rock and expose the bone hidden inside, or finer tools like dentist picks, little brushes, or little scalpel blades to actually remove all the sediment and be able to extract the bones out of the rock. And here, these are the three feathered dinosaurs that were discovered. They're called ostrich mimic dinosaurs for obvious reasons. They look very much like ostriches, but they have long tails. And they're not related to modern ostriches or any modern birds. It's a case of parallel evolution. Dinosaurs had adopted the same body shape as another animal, probably because they filled in a similar ecological niche. So you can see when fully grown, these ostrich mimic dinosaurs were between 3.5 and 4 meters long. So they're considered medium-sized dinosaurs. So two of our feathered ostrich mimic dinosaurs, or ornithomimids, are adults, these two here. And then we have a skeleton of a very young individual that was less than 1 year of age at the time of its death. So on two of the specimens, one adult and the juvenile, we found that on the body, we saw evidences of filamentous feathers. You can see those dark streaks there in the rock. Those are all the filamentous down-like feathers that covered the body, and they're identical to the feathers we find in China. So this means that these animals were covered with filamentous feathers for insulation to keep their body warm. But then the second adult didn't preserve filamentous feathers. They probably were destroyed during preparation back in the 90s. But we observed something that had never been observed in any other feathered dinosaurs before. Black markings directly on the bones of these forearms. They look like someone went with a Sharpie and started drawing on the bones. But no, those are true fossilized impressions. But impressions of what? If you look at the radius, just to orient yourselves, to the right, that's where the hand of the animal was. To the left is where the elbow of the animal was. So you can see the markings on the radius. That's the bone of the forearm on the side of your thumb. You can see the markings are more or less parallel to the long axis of the forearm. And whereas if you compare with the marks on the ulna, which is the bone that goes to your funny bone and to the pinky, you can see that the orientation varies, of the markings varies along the length. You can see they're nearly perpendicular to the bone, close to mid-length, but then they rotate to become essentially parallel to the bone as you get closer to the wrist. So what could those be? Well, I did a comparison with modern bird wings, and you can see that the orientation of the black markings in the ornithomimids is identical to the orientation of the rigid shafted covert feathers that cover the wing of modern birds. Now, we're not looking at the the flight feathers, like the primaries, secondaries, and tertiary. We're looking at the covert feathers up on top here of the wings. And you can see that these feathers have the same orientations as the markings in the ornithomimids. Around mid-bone, they're perpendicular to the wing. And as we get close to the wrist, they start changing their orientation to become parallel to the leading edge of the wing. So now we know that adult ornithomimids actually had wings, but the question is now, were wings also present in young individuals, in young ornithomimids? Well, if we look at the skeleton of our young individual, we see that it has one arm that's fully exposed and we don't see any feather impressions. So we can't answer that question there, but if we look at the second arm, you can see it's hidden under a lot of feather impressions. So if we look at a close-up of that arm, we may be able to answer if this animal had a true wing. So we'll zoom in on this area, and you can see here again the upper arm, forearm, and the hand hidden under the pile of feathers. You can see all those streaks there in the rock. They're all filamentous feathers. And if you look along the forearm, you don't see any differences. They're all filamentous feathers there as well. So it's telling us that ornithomimids that are at least 1 year, close to 1 year of age, did not possess wings. So they were wingless, but they were covered in filamentous feathers, body and arms alike. So based on these discoveries, we were able to update our reconstructions of the appearance of ornithomimids. Rather than having a very scaly lizard-like appearance, ornithomimids were covered with filamentous feathers to keep them warm, but they also had wings formed by rigid shafted feathers that were present only in older individuals. Young individuals were only covered in filamentous feathers. So, but what could wings be used for in an animal that's over 3 meters long, almost 4 meters long, that weighed several hundred pounds? It's obviously not for flight. So is this discovery consistent with any of the 3 hypotheses that had been suggested for the origin of wings? Well, if we look at them, we see that the 3 hypotheses, even though they seem very different, they all have one thing in common. They all predict that wings should be present in young individuals because they were essential for the survival of young individuals. But that's not what we see in ornithomimids. The young ornithomimids did not have wings, but adults did. So we need to reject all 3 hypotheses and find an alternative option for the origin of wings. So if we look at our fossils, what can the absence of wings in young ornithomimids, but their presence in adult ornithomimids, tell us about the function of wings in these early dinosaurs? Well, to answer that question, we need to figure out if the development of wings at an old age, namely individuals that are older than 1 year old, is it something that we see commonly in modern birds? Well, the answer is a resounding no. Wings develop at a very young age in modern birds. Among flying birds, wings develop in a matter of days to weeks, as you can see here is in this 12-day-old partridge that has already well-developed wings. So the early development of wings reflects the need and necessity to have functional wings as soon as possible for the survival of these animals. Among land-dwelling birds, such as ostriches, wings develop slightly slower, but they're nevertheless fully formed in a matter of weeks to months. For example, we have a 3-month-old ostrich here, and you can see that it already has well-developed wings. In comparison, the wing of ornithomimids are still absent on the age of 1 and probably developed on a time frame of years. So therefore, the wing of ornithomimids must have had a function that wasn't critical for the survival of young individuals, or else they would have never survived into adulthood. So a slow developmental rate, so a slow development that takes several years, is typical of characteristics that we call secondary sexual characteristics. So those are features like the lion's mane or the trunk of an elephant seal that actually develop slowly over time. So here in lion's mane, it develops it starts developing at about a year and a half of age and ends its growth at around 5 years old. And then in elephant seals, the trunk starts developing around the age of 4 and stops its growth around the age of 9. And it's only at the end of this growth period, when the structure is fully developed, that animals are sexually mature and reach reproductive age. So the wings of ornithomimids were probably secondary sexual characteristics. So what could they have used their wings for? Well, probably for similar functions to what ostriches use their wings for. They could use their wings for display and courtship to impress females, to scare away predators, to brood their eggs, or maybe even to protect their offsprings. So in short, ornithomimids would have used their wings for functions that started when the animal had reached puberty or sexual maturity, as we say in case of animals. And the wings would not have been useful for young animals. So what can the function of wings in ornithomimid or ostrich mimic dinosaurs can tell us about the origin of wings in dinosaurs and in birds? Well, if we look at this distribution of wings in the family tree of dinosaurs, again, to orient yourself, the more primitive dinosaurs are at the top of the photo, and the more advanced meat-eating dinosaurs, such as birds, are at the bottom. Well, we can see that ornithomimids are here in the middle, and they are the most primitive dinosaurs that we know that possessed wings. In comparisons, wings that were used for flying are found in the more advanced meat-eating dinosaurs, such as birds themselves and raptors, like animals similar to Velociraptor, but not Velociraptor itself. So the fact that wings being used for display and courtship, wings that are secondary sexual characteristics, are found among the most primitive theropods to have possessed wings. It suggests that the first wings did not evolve for gliding, for flying, or for climbing steep slopes. Rather, primitive wings first evolved in response to sexual selection for display and courtship. So try to impress a mate and try to scare away a competitor, something like that. So it's only later that through evolution that wings were co-opted for other functions, such as jumping up to try to capture prey, gliding from tree to tree, or climbing steep obstacles, and ultimately for flight in modern birds. But initially, wings evolved simply for show, simply for display and courtship. But later on, that's when they were co-opted for flight in birds. So once flight evolved, it allowed birds to diversify into a multitude of lineages that existed during the last 80 million years of the age of the dinosaurs. And most of those birds were birds with teeth. Modern birds are one of the rare lineages that didn't have teeth. And it's just that nowadays they're the only group that survives. So that's why we usually think of birds as being toothless. But in reality, during the age of the dinosaurs, most birds had teeth. Unfortunately, all of those lineages went extinct 66 million years ago at the same time as the dinosaurs, except for the lineage that led to modern birds. So unfortunately, going over all of those fascinating extinct bird lineages would take a long time and would be the subject of a whole new presentation. So I'll stop here and save that that overview of extinct birds for another time. But for now, I'd like to thank you all for being here tonight, and I'd be happy to answer your questions if you have any.
Wow. What an interesting view of the evolution of birds and obviously of dinosaurs too. Fascinating.
Here, I'm sorry, I'm trying to bring you back up up front. There you go. Now I see you. Yep, yeah, I see you. Oh, there's a question. What are your thoughts about the evolution of birdsong? That's a very good question. Lots of bird songs, they have a syrinx or an ossified or at least strongly cartilaginous part of the trachea. And that's what gives them the possibility to sing, like producing sounds. More primitive birds are capable of doing that. Any animal is probably capable of doing that, but really, like singing, like bird songs, that's something that, unfortunately, yeah, that part doesn't fossilize very well, so we don't have a very good sign of it. But I think it's last year or 2 years ago, someone was looking at fossil bones that are found in the throat of armored dinosaurs, not even closely related to birds, and they found similar types of bones as what you find in bird song. So it suggested that maybe some dinosaurs, namely some armored dinosaurs, were actually capable of producing songs, quote unquote. We don't know yet if they were as good as modern birds, but it sounds like the ability to produce sounds and maybe a melodic sound was actually it actually evolved in dinosaurs. We don't know if it's a case of parallel evolution, that armored dinosaurs evolved that ability separately, or if it's something that's common to all dinosaurs. But yeah, we know that at least some armored dinosaurs that are plant-eating dinosaurs were capable of producing songs, or we think that they were songs, but melodic sounds. And among meat-eating dinosaurs and the lineage leading to birds, fortunately, we haven't found anything that there. We don't have, well, the thing is, we don't have many good specimens that would preserve the syrinx. So it's probably something that evolved truly in birds. Even primitive birds may not have been songbirds. They would have been able to produce sounds, but probably not songs. And that's probably something unique to songbirds now, modern songbirds. But yeah, I mean, we're always one discovery away from changing everything that we know about the evolution of those things. So it's possible that maybe next week someone will announce the discovery of a syrinx or something like that in another dinosaur, and then yeah, we'd have to reconsider what we think we know about the evolution of birds and songbirds.
I see a question there from Uli. Do you want to unmute and ask your question, Uli?
Yeah, great talk, very interesting. And I have a question. I mean, we have seen that over the decades, the view on dinosaurs has changed quite dramatically. My question is, going a step back about the evolution of feathers. Anybody has looked into the evolution of feathers in respect of becoming warm-blooded, because flying is a high energy activity that really only homocerns like the birds can master. So maybe the feathers are the first step in becoming more weather independent.
Oh,
Is there
yeah,
any
absolutely.
insight into that?
Yeah, absolutely. It was long. We always thought, okay, we know birds are warm-blooded, mammals are warm-blooded. Everything else is quote unquote cold-blooded or ectothermic. So it was thought that dinosaurs were probably cold-blooded, but then that's because we were mainly dealing, at least in the early 20th century, dealing with very large lumbering beasts that we thought lived in swamps, so we thought they were cold-blooded. But since the early 70s, we started finding fossils of meat-eating dinosaurs that seem to be highly active animals, like the raptors. They seem to be like not slow-going animals, but really animals adapted for speed. And if you want to be fast all the time, you need to be warm-blooded. So there's different lines of research. Some you looking at the chemistry of the bones, try to answer whether dinosaurs were truly warm-blooded, like birds or like mammals. And the answer is yes and no. They were warm-blooded, but not the same way that modern birds and mammals are, because that's really very costly to be warm that way. You need to eat a lot of food. You need to eat constantly to be able to produce your own heat. But dinosaurs were kind of intermediate. They managed to be warm-blooded, but still with the kind of a mechanism that's more closely related to what cold-blooded do, so cold-blooded animals do. And now yeah, we find that even the first birds were not warm-blooded the way that modern birds were, yet they were capable of flying and they were active. So it shows that yeah, the way us mammals and birds evolved warm-bloodedness or endothermy is really just one way of being highly active animals. So dinosaurs have been doing it differently. And yes, the feathers, at least all the filamentous feathers, those we find among the most primitive dinosaurs, they cover all their bodies. So we think that yeah, filamentous feathers serve the same purpose as down feathers. It was to keep the body warm. But even before that, and that's probably even true for the evolution of hair in mammals. Now we usually think of hair as being a way to keep mammals warm, but the first hair in the ancestor of mammals would probably use as whiskers to basically probe and feel their surroundings, and then they realized that through evolution, the more they were covered with that, they have better sensation. But hey, it also started keeping them warm. So it's probably the same thing that happened in the ancestor of dinosaurs or the very first dinosaurs. They probably had evolved primitive excuse me, feathers that were used either as sensory motions or maybe even for display to basically grow a little mohawk on top of its head. And then later on, yet the coverage spread throughout over the body, and then it turned up that basically it kept the animal warm and gave it an advantage over other animals that weren't fully covered in feathers. So yes, first feathers were, when the animals got fully covered with them, was definitely for insulation, but you can't reject that these animals probably used it also for display, for courtship and display, to differentiate between species, to be colorful, to attract a mate, and things like that.
Thank
Pleasure.
I have a question.
Yes.
I find it just fascinating to think that wings originally developed to attract a mate, when I guess the law of averages would say that there's, an equal number of females as there are males. So it must have meant that the males wanted to get lots of females for wings as well as just colorful feathers to be used originally for that purpose.
Yes, well, we often think of males doing all the work and basically having to be showy to attract females. But in nature, it's rarely a one-sided thing. Females also have some power. They actually use their own feathers even to attract them, even though it may not be as flamboyant, as colorful as males. They also use their wings to attract mates, to select mates, and for other purposes. So yeah, so it's not we can't only attribute it, okay, feathers evolved because males were doing that, because oftentimes females also select. They may attract a lot of males and then be more choosy once they're there. Okay, which one am I gonna pick based on which one is more colorful? But usually it goes both ways. It's not only males that would have used their wings for displaying courtship. Females are also involved in what we call sexual selection, which is basically using attributes to try to impress a mate and to basically to choose which mate she's gonna join with to have offsprings. So it's not like we would expect to have wings only in males. They would have been just like in ostriches. Today, wings are present in both males and females, but males are usually the showier ones when it comes to display. But that doesn't mean that the female necessarily doesn't use its wings for courtship either. It just basically she does it in a different way.
Thank you.
My pleasure. So I see a lot of people saying thank you, great talk. So thank you so much. I really appreciate it. Hopefully it was a little change of tone. You used to seeing presentations about modern birds. I hope I was able to give you a little bit of perspective about where the birds came from and why they are the way they are, and where they got their wings from, and how they learned to fly.
Just thank you so much. Your passion for the subject is so infectious. It's wonderful. It really is.
Well, it's how, well, yeah, I'm one of those kids that actually never grew up. I was fascinated by dinosaurs when I was a kid, and I was too stubborn or too stupid to change my mind. So I turned it into a career. So yeah, I love it. It's
great
one of the
news.
greatest jobs, although I'm sure everybody in their own career think that they have the greatest job, but I really enjoy it. Even after all those years, I still enjoy it.
That's fantastic.
Oh, someone's asking you if the recording will be available later.
Yeah, yes, it will be. It'll be usually a week or so until we can get it put up, and it will be emailed round to the paid members of the society, and it'll also be a note on the Facebook page, etc., as well, to the Facebook group members.
There, I switched you back to being the host.
Oh my God, I have the power. Again, thank you so much, Francois. I really appreciate it. Hope to be traveling again next year, and you might see us in the museum then checking it out, because we're looking at some time in Alberta by the looks of it.
Yeah, and we have modern birds over here as well. So lots of mountain bluebirds. I'm not a bird watcher, so I can't tell you all the species, but we have lots in the Badlands even. So you can hit two birds with one stone. Maybe that's a bad saying, but you can come see the Badlands, see fossils, and see birds that we have in the province at the same time.
Well, we'll check it out. We've been out there before, so we'll check it out again.
Can I just ask?
Thanks, everybody. Please don't forget to check out the events page for up and coming information. And to put it bluntly, let's get out there and check these migrants out. Oh, Susan, you have a question. Oh, you're
just waving. Okay.
Oh, okay.
Bye. Thank you so much, everyone.
Thanks, everybody. Have a great evening.
Have a good night. Bye.
Thank you. Bye-bye.